Okay, so let's start where we left yesterday. So remember in yesterday's courses we play a game, right? A game. So it's that we toss a fair coin, and there are two cases. So the coin can get a head or a tail, and if it gets a head, we stop it, and if it gets a tail, we continue to toss, and if it's head again, we stop, right? And if it's a tail, we just continue until it reaches a head. And in yesterday's lecture, we found that the probability that we toss a head and stop is 1/2, and the probability to get a tail and then a head is 1/4, right? And this is 1/8. And also in yesterday's lecture, let's recap. So to verify that this is the correct probability, right? We added the probability of all cases, right? Because the case can continue, right? We can get a lot of t and then one head, right? And this is like 2 to the power of n, right? So n is the total number, the total length of the sequence. Okay, so in order to verify that this is a correct probability distribution or a correct probability, we add them all together and we found this is exactly 1, right? Okay, so maybe Emma Yu, can you help me get the expected value of length, right? So by length, this have a length 1, right? This have a length 2. So you don't need to get the answer, but do give me an expression. Yeah.
Uh, I like
Let me give you a hint. So what is the expected value? So expected value is just value times its corresponding probability, right?
yeah.
For age, what is the value and what is the probability?
Uh, 1/2 times um 1/2. Wait, no.
Like what is the value for age?
Uh, one.
Yeah, it is 1. So it's expected value of length, right? Age has a length 1. So the value is 1, right?
Oh,
And
okay,
what?
now I remember.
Yeah, yeah. So first find the value and then find its corresponding probability. So what's the probability of age?
1/2.
Yeah, 1/2. Cool. And can you get the second term? Like what is the value for TH and what is the probability for TH? Yeah.
3 times 1/4.
Yeah. 2 times 1/4. Correct? And what is maybe like I'm not sure. Can you guess the third term?
Um, 3 times.
Yeah.
No. Yeah.
3 times what?
Uh, 1 divided by 8.
Yeah. 1/8, right? Because the
Yeah.
probability that this appears is 1/8. Yeah. So we can continue like 4 times 1/16 plus dot dot dot. Yeah. So then what is the value of this, right? Okay. Instead of giving you the answer directly, I really want you to work this out by yourself. So get a piece of paper and a pencil. Let me show you how we find like the value of this yesterday. So try to learn, right? Try to learn this. So suppose x equals 1/2 plus 1/4 plus dot dot dot, right? Plus 1/8 plus dot dot dot, right? Then we find the 2x equals to 1 plus 1/2 plus 1/4 plus dot dot dot. And then we have 2x minus x equals, so this and this cancel out, right? So it's just 1. And we found that based on this equation, x is equal to 1. So then we know that this expression has a value of 1, right? So this is an example. And I can give you even a further hint. So now, again, right? We can let x equal to what? We can let x equal to this. 1 times 1/2 plus 2 times 1/4 plus 3 times 1/8 plus 4 times 1/16 plus dot dot dot, right? Then think, then what is 2x, right? Try to think of it this way. And I will give you around 4 to 5 minutes to work this out. The reason I'm not showing you the answer directly is that we already made a similar like math expression, and we already show one way to figure it out, right? And it's actually not that different. I mean, of course, this one is it's a little bit harder, right? It's not much harder. It's a little bit harder, but still you can use the same method to find the value. And when you are calculating expected value and calculating probability, this kind of calculation, this technique will appears again and again. It's quite classic. So I really want you to be able to work this out. I'll give you 4 minutes. Okay, so maybe Jason, do you have any thought?
Um, so then we have x equals this, then we have 2x equals 1. No, yeah, 2x equals like 1 times 1/2 times 2, which is just
Yeah,
uh
1 times 1. Yeah,
times 1/2 plus 3 times 1. No, no, 2. No, 1 plus 2 times 1/2 plus 3 times 1/4
yeah.
plus 4 times 1/8. And then if we 2x minus x, we just get 1 plus 1/2 plus 1/4 plus 1/8, which should be 2.
Yeah, so 2x minus x equals 1 plus 1/2 plus 1/4, right? Plus 1/8 plus dot dot dot, right? And this is equals to 2. The reason is that we already found the answer for this, right? So this is 1 and plus 1 is 2. So then we get that the value of x is equals to 2, right? So this is exactly what we are trying to find here, right? The expected value of this game is 2. So this is actually quite nice, right? So if we think of this game, right? So if we throw something, it's head we stop. If it's not head we continue, right? So we can throw like the coin like forever, right? You can always get tail and tail, 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 and then we may be very unlucky and throw a very long sequence. But but right, but expectedly, or like if we throw a lot of time, the average length of all our choice or all our attempts is just 2, right? So meaning that we'll throw like 1. So we'll get ahead and stop there. So the length is 1, right? So we get a length of 1 most of the time, or like 1/2 of the time, and we get a th like 1/4 of the time, and for the remaining 1/4, right? So we seldomly get like 3, 4, 5, or even 7 lengths, right? So even if we can get a length that is really long, but since the probability is too low, right? The probability, so you see the probability decrease exponentially here, right? So we may be very unlucky and get a length of 8 or length of 9, but the probability is 1/2 to the power of 9 or 1/2 to the power of like 8, 9, 10. So that will be very small and contribute little, right? Contribute too little to our expected value, and it will like hardly influence the expected value of the length. Yeah. So, and we eventually found out using math deduction that the average length of all our attempts is just 2, right? So mostly we will success in one, like after tossing the coin 1 times or 2 times or maybe 3 times, but seldomly get like 4 times, 5 times, or 6 times. Yeah. So that's the main idea of this game. And actually, let's see even harder game. So say in another game, right? So for this, I won't give you any hint at all because it's a similar game. So I will give you 5 minutes to try to work this game. Okay. In another game, say we're still tossing a coin, and if we get an H, right? We won't stop it there. We'll try. We will throw again, and it may be T, and it may be T, and it may be an H again. So only if we throw 2H, right, consecutively. You see, only if we throw 2H consecutively, we'll stop. And if we throw H and an H, we stop. If we throw T, 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 and H, and then T, it does. Then we kind of need to try to accumulate H again. And if we make 2H in like 2H, like a 2 adjacent H or 2 consecutive H, we stop, right? So this game seems a little bit more complicated, but still we can work it out by finding what. So what is the case when if we need to stop the game, we have to at least toss 2 times, right? So this is a length 2. So what are possible scenario for length 3? So it can be THH, right? And can it be HTH? No, because HTH won't stop there, right? And what is possible ways for length 4? It can be TTHH, right? Or it can be HTHH, because if you throw an H and a T, then that doesn't count. Can it be THHH? No, it can't, right? So it's because if you have THH, you already stopped there, right? So for length of 4, we have like two possible ways, right? TTHH or HTHH. Yeah. For length of 5. So in order to find the case for length of 5, if you want to stop the game, you must have a 2H consecutively at the very end, right? So for the first 3, it can be OT, right? It can be OT. And also it can be like a THT then HH, right? And it can also be HTT then HH, right? So maybe more cases. Yeah. So this is a little bit complicated. Try to think like how to find an expression for this game, right? So basically we need to calculate several things. So if we have a length 2, right? If we have a length 2 case, what is the total probability for length 2? And say in this case we have a length 3, right? What is the total probability for length 3? I mean, I can give you the answer for the first one. For last 2, it's of course 1/4, right? Because we threw 2H. 1H is 1/2, and the other H is also 1/2. And you multiply them together, you get 1/4. And for the last 3, you also only have one choice, right? It cannot be HTH. It can only be THH. But for length 4, it's more complicated because you have 2 cases and you need to add the probability together. And what about length 5? What about length 6? What about length 7, right? So I won't. So I will give you 5 minutes, and you just think of lens four, lens five, and lens six. Yeah, just think about these two cases, and once you figure out lens six, and maybe even maybe just lens five, I think you may already get the pattern, and could answer the question for general n. Right, general lens n was a probability. Yeah, so I'll give you 5 minutes to work on this problem, and I will not give you any hint. This is just for you to try to practice how to calculate a probability. Yeah. Okay, so let's get back to this. So, what's the probability for length three? Maybe like Phoebe. Do you know what's the probability that we get a length three?
Um, uh, uh, 1 divided by 8.
Yeah, 1 divided by 8. That's very good because for length three we only have one case, right? And in order to get a THH, T is one half, H is one half, and the other H is one half. So we have only one possible way to get a THH, and it's 1 divided by 8. Yeah. And maybe for Hector, do you know what's the probability for length four?
1/16.
Remember that length four we have two cases, right? TTHH and HTHH are both length four. So what's the total probability of getting length four?
Also 1/8.
Yeah, it's also 1/8. Yeah, because this is so the only thing we care about is how many times we toss a coin, right? So in both cases we toss the coin 4 times, so we need to put them together. And good. And Mark, do you know what's the probability for length five? First, you need to count how many cases are there for length five. Maybe you can answer this first.
So there are 3 cases, and one probability is like 1/32, so it's 3/32.
Very good, but can you explain why there are only 3 cases here? So I mean at least 3 cases. So why are them like all the cases?
Because the last two has to be HH, or
Yeah.
else it would end like earlier than 5. So
Yeah.
and the third one has to be T,
Yeah.
because so the only two like positions that matter is the first and the second.
Yeah.
And there are only like 3 options, which is like TT, TH, and HT.
Yeah, because it cannot be HH, right? Otherwise it stop at the like a second position. Yeah, that's very correct. And you sort of get the idea, right? So you use 2 times this and 3 times this and 4 times this and 5 times this, and you may think, okay, this is so ugly and it has no pattern, so we could probably not find like the answer, right? Because we don't see any patterns here. Yeah. Okay, so then what do we do, right? What do we do? Let me teach you another technique for calculating expected value. So think of the game as we want to find an expected value. So I use E to like represent the expected value. So expected value of what? I will put it into the parentheses. So we want to find the expected value of number of toes, right? So number of toes until HH, right? Until we get to H in consecutive order and we stop. Okay, so then how do we get H and H? So we first must need to like throw like so in order to get to H in consecutive order, first we need one H to appear, right? So we need one H to appear, and then for the second position, it can be either T or H, right? So it's like we can make this into another language. So number of toes. So until HH, right? So until HH can be explained in two ways. So it can be either like we first get an H and then an H, right? So this is the case where we get to H. And what's the other case? The other case is that we first get let me think how to express it. So so we first get an H, but however we are very unlucky because if we get an H here, then there are two things possible. So the next one can be H, or the next one can be a T, right? First get an H, and then a T. Okay, so these are two cases, right? So then we can say it can either be the number of toes until HH, right? Until HH. So and so number of toes until HH. So it can be written this way. So first we get the length, right? Get the length. Number of toes. Number of toes. When we first number of toes when an H appears, right? So the first H appears. Okay. So if an H appears and then we get another H, so then we just need to add the length by one, right? So get another H. Okay. Then we can stop here, right? Because say in this case we get TTH and then we get an H, right? Then we stop. Then we can stop. Okay. And the length is just number of toes when the first H appears, and then we plus one because this one means another H. But this does not always happen. Why? Because it's after an H appears, we not necessarily get an H, right? How many probability? So what's the probability that we get an H after an H appear? Amma, you can answer this question. So for example, an H already appears. So what's the probability that we get another H?
1/4.
Oh, so we are assuming an H already appears. So what's the probability of getting another H?
Oh.
It's only one half, right?
Mm-hmm.
And you see why you should not use 1/4, because this one, right? This have a length, right? So we are not assuming that H just appears like free. H doesn't appears free. So number of toes when H appears is not one. It's actually it can be like T T T T T T T H. It can be very long, right? So so this is exactly the example we work out here, right? So it can be very long. So the length here can be very long. But we are like taking it as a given. So whatever it is, it can be a very long stuff, right? So first we need to assume that an H already appears, and we look at the second position or the next position. It can be either an H or a T, right? So if it's an H, it has 1/2 probabilities, and it also have a 1/2 probability of getting a T, right? Yeah. So then in this case, do you agree that we eventually get to H? First, we need like one H appears, and then luckily another H appears, right? Do you agree on this?
Mm-hmm.
Okay, so then let's think of another stuff. So say first we get E number of toss, right? So so we are always like toss until an H appears. Why? Because we need two H. So if like one H doesn't appear, then we need to toss again, right? So we need to toss until at least one H appears, right? So this is still E number of toss when one H appears, right? When one H appears, yeah, number of toss when one H appears. And when one H appears, we stop there, right? So it can be rephrased as number of toss until one edge appears, right? This is also number of toss until one edge appears. Okay, so this is already a length, right? This length can be very great, but it's a length. Okay, so one edge appears. What's the probability that a t follows? I'm not sure can you answer this question.
Uh, 1/2.
Yeah, so +1. So it's also +1, right? Times 1/2. Okay. But if a t appears, could this be like a number of toes until HH? No, because a t appears, we did not get HH. So we still need to plus, right? So we still need to plus. We need to plus the length that we eventually get to H, right? So for this one, the length is just this +1 because this is the number of toes until one H appears, right? So I need all of you to follow this very strictly because this is like a very convoluted or very smart way of thinking. So this is the expected length that the first H appears, right? So we're not saying that when H appears and then followed by T and then H appear again, right? No. We are talking about exactly the situation when the first one appears, right? So we call it until. So this is the number of toes that the first H appears, right? If the first H appears and then we get an H, we can stop the game, right? And the number length, the length, right? The length is just the length of this +1, right? Because this is the number of toes until one H appear, and we just need to toss one more time, and we get if we get an H which has a probability of 1/2, we can stop there. So the total number of toes is just the number of toes until one H appears +1, and this one means an H, right? But if we are unlucky, we first toss the expected number of toes until one H appears, and then we toss. So for the next move, for the next toss, we get a T. This also have 1/2 probability, right? So we times 1/2 there. But why do I leave this blank? Because then if we have toss a lot of times and until one H appear, and then we toss a T, we need to toss again, right? So in this case, we are very unlucky. We toss a T and we need to toss again. Then how many times do we need to toss until 2H appears? Think about this question. Can someone fill this blank? Try to view this equation as a whole. Can someone fill this blank? I'll give you 2 minutes to think about this equation, right? So this is an expected number of toes. So on the left hand side, it's the expected number of toes, like until we toss 2H in consecutive order. And then in order for that to happen, we can either first toss the number of toes until one H appears, and then we are lucky and we toss another H, which happens with 1/2 probability, right? So it can be either this case, and this case happens with 1/2 probability, or we can also get 2H when we first toss a 1H and then toss a T, right? So this can also happen and with 1/2 probability, but we still need to plus something. Why? Because if we toss until one H appear and toss a T, then seems that we need to start over, right? Seems because you have a T and the H here doesn't count at all. And we still need to toss. Then how many times do we need to toss in order for 2H to appear? Okay. Hector, do you know how to fill this blank? I give you hints. It will be something that already appears in this equation. Do you know what will that be? So it's not something that you need to invent or come up with. It will be a value that already appear in the whole equation. I can hear you. Do you have any thought? Sorry, I didn't hear you. Okay, maybe let's ask Mark. Mark, do you know what should we fill in here?
One, I don't know.
I mean, of course, it's at least two, right? Because we already toast a t, and if you just toast one time, then it's just an h, right? And of course, we don't get the number of toasts until 2h. So left hand side and right hand side needs to be equal, right? So this needs to be the expected length that we get 2h, right? So in this case, so it's probability times the value. So in this case, we get 2h, right? And the 2h happens with 1/2. And in this case, we also need to get 2h, right? And the probability in this case is also 1/2. Okay, so then what should this be? So this should be at least 2, right? So it's a number of times that we need to get to h. And let me give you the correct answer. The correct answer is that you just copy this again, right? Why? Because this is the number of times you toast until 1h appears. It may be a lot of times, right? And then suddenly a t appears. What does that mean? That means all your effort doesn't count at all, right? You need to toast again. Toast how many times? Toast exactly the number of times that 2h appears, right? So you see, on the left-hand side, we are calculating the number of times, the expected number of times, the expected number of toasts that 2h appears. And this is exactly the same case here, right? If you toast until 1h appears and toast a t, then you need to toast how many times? Toast exactly the number of times that 2h appears, right? So if you put this here, the two equations equals. Emma Yu, did you get this equation?
Wait, can you repeat the question again?
I mean, the question is that this and this are equal. So do you know why the left hand side and right hand side are equal? Do you get that they have equal value?
Oh,
No, right? So then let me explain. Okay, so let me work this out. So what is the expected number for toast until 2h happens? As we said, right? So expected value is just value times the corresponding probability, right? That value happens, right? So something and something happens. And this value could be what? So this value plus value, right? Like the value 1 times the probability that value 1 happens. And we can call it a probability of value 1, right? And the value 2 times the probability that value 2 happens. Okay. Dot dot dot, right? So this is this is definition of an expected value. Okay. So in our case, like when you calculate the expected value like this, then you have an infinite number of value, and you need to find the infinite corresponding probability. So like 2 times 1/4, 3 times 1/8, 4 times 1/8, 5 times 3/32. It's tedious, right? You have infinite value, and each value have a probability. You need to multiply them all and add them together. But actually, when you count the number of toes until 2h happens, you can divide only by 2 cases. So this is in this perspective, in this thinking, you are dividing the cases by the matter of length, right? So you can toast 2 times when 2h happens. You can toast 3 times when 2h happens. You can toast 4 times when 2h happens. You can toast 5 times when 2h happens. And each number of times you have a probability, right? So, but you can toast infinite number of times before 2h happens. So you have an infinite number of values, and each value has a corresponding probability. Ama, do you understand this? Like the way of calculating using this?
mm-hmm.
Yeah, because we are calculating the expected number of lengths, right? The expected length, right? Expected value of length. So we are dividing the case by length, right? It can be length 2, length 3, length 4, length 5. Okay, but instead of looking at it that way, we can think, okay, this is still the expected number for, so this is also, we can say expected length until 2h, right? So by length, we actually mean the number of toes, right? How many times do you toes? This is the length. Okay, to calculate the expected number of toes until 2h, we can calculate two stuff. So we have also the expected number of toes, right? So we can toes a lot of times. Expected number of toes until HH, right? So it's still expected number of toes until 2h happens. But in this case, it's like when we first get an H, we get another H immediately, right? So in this case, we can calculate the expected number of toes when this happens, right? So you get an H and you get another H. So it's like you get a lot of T and suddenly 2H appears, right? So we are calculating the expected number of toes when this happens, and yeah, and how to calculate the let me think how to say this, and yeah, and how to calculate this, right? So let me see the value of so actually let me write it this way. So it's the value here is the total number of toes, right? The total number of toes, or we can write it this way. So the value here is also the length, right? Length of the case, length of case one times the probability of case one. And what is case one? Case one is when you get an age in the first time, you get another age immediately, right? And what is the probability that when you get an age in the first time and then you get an age immediately? It's 1/2, right? Because we assume you already get an age. What's the probability that you'll get an age immediately? It's just 1/2, right? Because you can either get 1/2, or you can either get an H follow or get a T follow, right? Okay. So the probability of case one is just 1/2. And what is the length, right? What is the length, or we call value, right, of case one? So the value or length of case one is just how many times do you toes until you get a first stage and then get an H immediately. Emma, you can answer this question. So say we get an H for the first time, and then we get an H immediately. What is the total number of toes?
2.
No, we first need to get an H.
Uh-huh.
In order to get an H, you cannot just throw an H, right? You may throw a lot of T and then get an H, right?
Uh-huh.
So what's that? That is the expected value that you get an H, right? It's expected value, expected number of toes. You toes a lot of time and you get the average of that, right? It's the net expected number of toes that until a first stage appears, right? So what's the value actually? The value is actually exactly 2, right? We already found that you can toast like 1 times and then you get an H. The probability is 1/2. And you can also toast 2 times T and an H. The probability is 1/4, right? You can also be very unlucky toast like a 10T and then an H, and the probability is just 1/2 to the power of 11, right? So what is the expected number of toes until 1H appears? It's just 2, right? Emma, do you get this?
Uh-huh.
Yeah, but this is the first time you get an H. But in order for you to get 2H, how many times do you need to toast? Emma, you can still answer this. I mean, this is the expected number of toasts that you get 1H. So how many number do you need to toast if you want to get 2H?
Is the answer like a phrase or is it like a specific number?
You need to modify this. So it's just +1, right? Because in this case, we assume you get an H in the first time, and then you get another H immediately. So it's just the number of times you toss until an H. And then you get an H immediately, which means one extra toss, right? So the total number of toss for the first case is just number of toss you get an H, and then +1. Do you get this?
Uh-huh.
Yeah. So this is and this have a number, right? This is actually 2 + 1. This is equals to 3. Yeah. Why? Because you for number of toss until you get an H, this can be 1, right? You toss and then you get an H. It can also be 2. You toss a T and then an H. It can be 3. You toss TT and then an H, right? So it's all kind of cases, right? All kinds of cases. But its average length is 2. We just show here, right? It's 1 times 1 over 2 plus 2 times 1 over 4 plus 3 times 1 over 8, right? You have one half probability to get an H immediately. You have 1/4 probability to get to toss 2 times before an H comes. You have 1/8 probability to toss 3 times before an H comes, right? So the average number of toss in order for a first H to appear is 2. This we already calculate. Do you get this, Amayu?
Mm-hmm.
Yeah. And so we need to toss until the first H appears. And we just calculated it's just so the average number of toss for the first H to appear is 2, right? So we just calculated in this case, right? So 1 times 1 over 2 plus 2 times 1 over 4 plus 3 times 1 over 8 plus 4 times 1 over 16. This expression has the value of 2, right? So we already get this. And this is exactly the average number of toss you need to toss until the first H appear. And then you have, and after this, you have a 1/2 probability that an H follows immediately, right? So then the total length in this case is 3, right? So case 1 is that you toss, then you get an H, and then you get another H. This is case 1, right? So case 1 has an expected number of lengths of 3, and for case 1 to happen, since you already get an H, the probability of get another H is 1/2, right? So the number of toss to get 2H is just 3 times 1/2. But this is not the whole case, right? Because you can toss and get an H, and then you are unlucky you get a T, right? This also have 1/2 probability. So we call this case 2. So case 2, when you get an H in the first time. So a lot of you may be curious on why the probability here is like 1/2, because someone will ask, isn't it like you also need to give a probability that you get an H in the first time, right? So I mean an H follow this H is 1/2. Everyone understand this, right? But we think like it also takes a probability when you get an H in the first time, right? So you may be curious on this. So after we get an H, of course it's the 1/2 probability to get another H, and the 1/2 probability to get another T, right? I think everyone agree on this. But some of you may get confused, thinking that why when you calculate the probability of case 1, you don't consider when you get an H the probability of when you get an H in the first time. The answer is the probability that you get an H in the first time is 1. So it's 1 times 1/2 and equals 1/2. Why? Because when you toast, right? When you toast, you will eventually get an H, right? So this doesn't mean that you get an H and do something else. This means that when you get an H in the first time, it doesn't restrict on the number of toes you make. I mean, you can make 2 toes and get an H in the first time, and this has a probability, right? This is TTH, which has probability 1/8, right? In this case, see, it is TTH, then the probability is 1/8, and you can get the H for the first time when you make 2 toes, and the probability is 1/4. But we are saying that you are getting an H in the first time. So we don't restrict, right? We don't restrict on the last. You can either be this H, or you can be TH, or you can be TTH, or you can be TTTTTTTTH, right? And we just said, when you sum this all up, the probability is 1, right? So when you get an H in the first time, this statement, right? This statement has a probability equals to 1, because you will eventually get an H if you toast enough number of times, right? So maybe like Amasher, do you get this?
Yeah.
Yeah, very good. So when you get an H in the first time, this doesn't influence your probability because you will eventually get an H. The only thing that's influencing your probability is that after you get an H, what is the next number, right? The next number can be an H, which happens 1/2 probability, or it can be T, which also happens with 1/2 probability. And these are exactly just two cases, right? Because when you get H for the first time, there are only two cases following. Case 1 is you get an H immediately and then you stop the game. Case 2 is you get a T and you don't stop the game, right? But it also happens with 1/2 probability. Okay, so when you get an H in the first time, so this is also high probability 1, and you get another T, right? And this has a probability 1/2. But what is the last? I mean, the last in the first case, when you get an H for the first time, we already know that the last, right? The average length is 2 for this, right? Because when you get an H for the first time, we already calculated the average length here, right? So 1 times 1/2, 2 times 1/4, 3 times 1/8. So the average length of the first case is like a 2. So when you get an H for the first time, it's 2. And then you get another H. So another H means another toast. So the total number of toasts for the first case is 3, right? And when you get an H in the first time, this length is 2, right? Because you can either get a length 1, you can either get a length 2, length 3, length 4. Those are all possible, but with different probabilities. And you times the probability and you sum up together, you get the answer. The average number of toasts you made to get the first H is 2, right? And you get another T, and this is another toast, right? So 3 toasts. Okay, and but you get a T, so you are very unfortunate, right? You need to toast again. So how many toasts do you need to get until 2H? This is exactly our original problem, right? Because you toast a lot of number of times, and the average number of times is 2, right? And you get an H, and you toast a T. This makes like a completely eliminate the usage of the first stage, right? Because you toast a T, and then this first stage doesn't count. You need to toast until you get an H. How many times you need to toast until you get an H? The average number is exactly the same we want to find. Do you under this, Emily?
Mm-hmm.
So can you explain the whole idea of case 2 again? Like in your own words?
When you get an H and then the probability equals 1 and then you get another T, you have to like start again to like the original equation.
Yeah. So once you get a T, the how many toasts do you need to toast, like how many extra toasts do you need to make in order for you to get to H? This is exactly the same question we are trying to find, because when you get a T, you are back to square 0, right? You are back to origin, because you get a T, then everything in front of you doesn't count. I need to start over again, right? When you start over again, like this is exactly the original problem. So from now, it's like you haven't make any toast at all. How many toasts do you need to get to H, right? So this is exactly what? This is exactly the problem we want to find. So in this case, how many times do you toast to get to H? You first toast an average number for 2 times, right? Because this is the average number of times to get a first H is 2. And then you toast a T, which plus 1. This is 1 extra toast. And then you need to toast exactly the number of time that's needed to get to H, right? So this is the total number of toasts for case 2. So do you agree with this? I'm not sure.
Yeah.
Yeah. Okay. So case one has a probability of 1/2. Case two also have a probability of one half, right? So then it's like a length of the case one, right? So the value of case one times the probability of case one, and then is the length of case two times the probability of case two, and that's by definition of our answer, right? So for case one, we only need to throw an average number for 3 times, and the probability is 1/2. And for case two, we need to throw a probability of 3 plus e, like our original problem, and also times 1/2, right? So eventually we get an equation. How many times on average do we need to toss until we get to h? Is 3 times 1/2 plus 3 times exactly this value, right? Exactly this value times 1/2. And then we can solve an equation and get the value, right? Because this is an unknown, and it's exactly the same with this. And this 3 1/2 are all known value, right? So I will give you 1 minute to calculate this answer. Yeah, actually, I don't think you need 1 minute to do this to solve this equation. It's just a one variable linear equation. So maybe Jason, can you answer like what is the average number of toes to get 2h?
So then it should be equal to, let me see, 3/3 plus 1/2 of this 6, I think.
Yeah, exactly 6. Right. So you see, now you can calculate the expected length for very complicated problems, right? It is like you toss an h and then an h, you can stop the game. If you toss an h and then t and then h, you cannot stop the game. You need to toss another h. But if you toss t again, you need to start all over again, right? So this game is a very, very good. Yeah. And let me give you some background of the game. So this game is like actually interview questions if you want to join hedge fund. So you see like hedge fund when you want to be a trader or a quantitative researcher. So meaning that you want to trade stocks professionally. You need to be really quick at math and calculating probability, right? Because they are calculating probability. What's the probability that you make 10 million? What's the probability that you make 1 million? And what is the probability that you lose 1 million? What's the probability that you lose 10 million, right? You need to calculate all this probability. And then you need to calculate your expected profit. So on average, so consider all the cases. There are good cases, there are bad cases. There are when some war happens or like some trade is made between like two different countries, right? You need to consider all kind of cases, the probability of all kinds of cases, and then make a decision on the expected profit that you made. Okay, so in this lecture, in the first half of this lecture, we only talk about the expected value, right? So which can help you calculate the expected profit. But when you want to be a professional trader, you also need to consider about risk. So even if you have an expected profit of maybe 10 million, you won't even try if you face tremendous risk. So I mean, on average, you will make a lot of money. But if you face like a 50% like a probability of lose and lose all your things, you won't even try, right? I mean, so say on 50% of changes, you will lose everything. On 50% of changes, you will win a lot of stuff, right? Say I will give you a concrete example. So say you have $10. In 50 per, so say $10 is all you have, and it takes a long time for you to earn $10. And in one case, if you bet on something, if you bet on something, you have 50% of chance to lose all your $10, and you have a 50% of chance to get $100. What's the expected profit to make? I mean, in this case, it's very simple, right? So then with 0.5% like a chance, you lose all $10, so your profit is -10, right? And with 0.5 cases or probability, you make $90. Well, because you invest $10 and you get $100, so your net profit is $90, right? So what's expected profit? Is just calculating this, right? Then you get 40, right? So 40 is greater than 0, right? So it's a positive expected profit, meaning if you bet on this game, on average you will win something, right? But most trading firms won't let you to use this strategy. Why? Because with 50% of chance you lose everything, right? Say $10 is your everything. Like it will take a long time to earn $10. So no company will risk with 50% probability to lose everything. So by losing everything, this means that the company goes broke, and like everyone get fired, right? And all your effort, maybe you spend 10 years to building all those strategies and earn a lot of money, and just because of this one single trading, one single bet, you lose everything. You lose all the like rewards, all your like names, all the stuff that you have accumulated in these 10 years, right? So this is too risky. Maybe with 0.00001% of losing everything, you may tempted to try, right? Yeah, but the perfect thing is that you have zero probability of lose everything. I mean, you can have a positive probability of losing something, but not a lot of things, right? If you lose something, you can take time to earn it back. But if you lose everything, you don't have enough resources, you don't have enough money to win again, right? Because you lose everything. I mean, if your net asset goes from $10 to $9, then you still have $9 to earn it back. But if your net asset goes from $10 to $0, you have nothing to earn back, right? Because you have nothing for you to enter the game again. You are like you exist the game like forever. Yeah. So this is the whole idea. So maybe in the next half of the lecture or in the next lecture we will go go deeply to how to calculate risk. So risk also have like mathematical names called variance. So variance means like the how the numbers goes in like a different direction. How the number diverge from the mean, right? The mean is the average, the expected. Right? It is what you expected, right? You expected the numbers to be very close to the mean, but in real world, this may be like different. The numbers can be very far away from the mean, right? So this means that the variance is so large. Okay, so yeah, enough of that. And so this is all the background of this problem. So if you can solve this problem, you are very likely to get into some famous trading firms in Wall Street. So this is actually a Wall Street interview questions. And of course, to go to Wall Street, you not only need to solve this probability question, you need to solve maybe 5 or 6 more additional questions. But I mean, being able to solve this is a huge step towards successful like finance career. Okay, so let's consider another game. Yeah, so you see we are playing a game again and again, right? Because like trading firms for Wall Street trading firms, they also like you to play a lot of game. And in one company called Discrete, the final interview, in your final interview, in your on-site interview, you actually get to play poker games with interviewer, and the interviewer will test your strategy of the poker games, and so you can't win by luck. So he will like constantly ask you the reasoning behind your strategy. So you cannot like I play without a strategy, or I don't know about my strategy. So he will ask you to actually calculate the expected earning, like the expected profit of your strategy, and also calculate the variance, which means the risk of your strategy. Okay. So let's consider. So for this, I will give you 10 minutes to think about this another game because it's very similar. And I hope that you can fully understand our method here and solve the game entirely by yourself. I will give you 10 minutes, and this 10 minutes can be treated either as a break if you think, oh, this is too hard, or if you think it's really interesting. I really encourage you to actually try to solve this game by yourself. Yeah. So the method is exactly the same as this, with a little adaptation or modification. Okay. So in another game, let's see the game. You're still tossing the coin, right? So we get really deep into coin tossing games. So you're still tossing a coin, and in this time so when will the game stop? The game stop when you toss two head in total. So it is different from this game. So for this game, in order to stop, you need to toss two head in consecutively, right? But for this game, it seems more like much simpler. So you can toss head, no stop. Another head, stop. You can toss head, no stop. A tail, no stop. And then a head. You stop there. You do not need to toss the head again. Or it's like a tail, head, tail, head. Stops there. Because you already tossed two head in total. So then the question is the same. What is the average number of toss? Or we use the word average and expected interchangeably. So meaning these two words have the same meaning. Yeah. So what is the expected number or the average number of toss you need to make until the game stop, right? So I mean, in this case, if you toss 2H in total, you stop, right? I mean, of course, in this game, you must, of course, still end with H, right? Because so why you must end with H? Think of this. Maybe Mark, can you explain why in this game we also still need to end with H?
I'm not sure.
Yeah, so I mean the rule of the game is like you need to toss 2H in total. But in order to end this game, you must toss an H at the very end. Maybe Emma, can you explain why we must end with an H?
Because the rule of the game is to end when you have two H's, so like to end the game you have to have like the second H.
Exactly. Yeah. So it means that you can end with T, right? Because you end with T, by ending the game, we need to 2H. It means that we already have so if you end with T, it means that you already have 2H. But if you already have 2H, you should end earlier, right? So you can never end with T, right? So in order to end the game, you must first have an H already, right? You must first have an H already, and then you may toss some T. But you must end with the second H, right? Because if the second H appears, you must end the game, right? So even if we do not say like you need to end with 2H explicitly, we still can infer from our rules that the game must end with H. Okay, very good, Emma. Yeah, this is a very smart observation. Okay, let me stop myself and pause the recording and give you 10 minutes to think about the game. Yeah. Yeah, so it's exactly 10 minutes. So maybe Emma, do you have any thought on this game?
The way I thought of it was basically we add like the expected value of like um getting one head and then like add on to the expected value of getting the second head.
Yeah, that's very clever. So first we need to get at least one age, right? And then it becomes the game of getting another age. Yeah, I think that's exactly the ways to do this, right? So then that means the expected number of the expected, but so yeah, so we can write it as this. So we expected the number of toes to get 2H in total. First, we need to get this is expected number of toes until 1H, right? I mean, this don't need to time probability because this always happens. And when 1h appears, then they still need the number of toes, right? Number of toes until 1h. Yeah. So then it becomes 2 plus 2 equals 4. Yeah, so you see, this is so this is not that hard, but it is sort of using the same idea of this, right? This is like much harder. This is like first you need an edge, and then you need an edge immediately, or you need an edge and you have a tail, and then it's just it's the same as back into the original questions. And this happens with 1/2, and this happens with 1/2 probability. And this is exactly okay. So now let's end here. I mean, of course, if you want to generalize a game or you want to try some practice, you can for both game you can try like 3h, right? For this one, I mean, for this one, 3h is just the number of toes until 1h and the number of toes until 1h and the number of toes until another h. Yeah, but for this one, what happens if you get the game will only end if you get a 3h consecutively? Yeah, and I mean that can be a brainstorm, that can be an extra problem if you want to try. But I think that's all. Okay, so let me copy all this stuff into our group. Oh, maybe later, and let me start another topic. It's called variance, or what we think as risk. Yes, so variance or risk. So how to calculate variance? Let's still using the coin example, right? The coin example. Say age means 1 and the tail means 0. And we already know that then the expected value, right? The expected value of coin is 1 times 1/2 plus 0 times 1/2, right? And actually, let's not use the coin. Let's use the dice because the value of dice is more clear, right? It's 1, 2, it's 1, 2, 3, and then 4, and then 5, and then 6 here, and the probability of everything is just 1, 6, right? 1, 6, 1, 6, dot dot dot, and 1, 6. Yeah. And we know the expected value, right? The expected value of dice is just 1 times 1 6 plus 2 times 1 6 plus dot 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 plus 6 times 1 6. And then this is 21 over 6, which means 3.5. Okay, so this is a average number when you roll a dice. And what is the variance? The variance by definition is that it's like you use value 1, right? You use so you can get a 1. How far is 1 from its average value, right? It's 1 minus 1 1 minus dice, right? And then you square it up. So why you square? So you square it up, right? So later I will ask you why we need to square it. And then it's 2 minus the average value, right? So it's each value minus the average value and the square. And so 6 minus the average value squared. And overall, we divide the whole stuff by 6. So there are two things I want to ask you in the definition of variance here. Actually, let me use this parenthesis, use square parenthesis for the outer side. Yeah. So inside is the number, right? This number minus the average squared, and this number minus average, this 3 minus average, 4 minus average, 5 minus average, 6 minus average, and we square each of them, and then we sum it all up. And in the end, we divide by 6. Okay. So this is a definition of variance. And maybe I'm not sure, can you give a thought on why we need to square it up? Yeah. Yeah. So what's your thought?
I don't know.
Or you can think of it this way. So what will happen if we don't square it?
Then
Try to calculate it. If you don't, so say we don't square it, then what's in the parentheses? Try to calculate. So
1 plus
yeah,
and until 6 and then minus like
So what do we got? So say it's not square. So then it's a 1 minus average plus 2 minus average plus dot 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 plus 6 minus average, right? So what do we get here? Try to calculate this. I mean, you already know the average number, right? The average number is 3.5. So what will happen if we don't square it and we just sum them directly? Try to calculate this. Yeah.
It would be 0.
Yeah, it will be 0. And the reason is like one so for one the difference between 1 and average, right, is negative, and the difference between 6 and average is positive. And actually 1 plus 6 is equals to average times 2, right? And 2 plus 5, 3 plus 4. This is all average double, right? So I mean, by average, it actually means so when you sum everything, it's the total number, right? The average is just the total numbers divided by the number for by the total the average just means the total sum, right? Total sum divided by the total numbers, right? So you get 0. But for variance, we want to calculate how far each number diverge from its average, right? So if we don't square it, we will get some positive and some negative, and they just cancel out, right? So we want to. So if you are negative, then you are still far away from average. If you are positive, you are also far away from average, right? So we want to make both positive and average. We want to make both positive and negative the same thing. So that's why we square. Do you get this? I'm not sure.
Yeah.
Yeah. So that is why we square it. And another question is why we divide by 6. Maybe Hector can you answer this question? So why at the very end we divide by 6? So here. Yeah, let me actually give you a hint. Yeah. So we already encountered all these questions in the previous 2 lectures. Because remember in the previous 2 lectures, what do we try to think, right? Try to think what? Think about square the square, right? The square loss function, right? Remember for the loss function we have several types. One is absolute loss function, one is a 1-0 loss function, and the other is a sum square, right? Square sum, or called square sum loss function. Yeah. And in square sum loss function, the square is like to find the distance, right? The square is to try to find the difference between the correct value, and also it penalizes like a very very far away stuff, right? For our variance, when we calculate risk, we also want to penalize far away stuff, right? Because 1 is very far away from average, and you square it up, it becomes an even larger number. So you also want to penalize far away stuff, because we are talking about risk. For risk, we don't want something that diverge too far from our average, from our expected value to happen, right? If it happens, it means a higher risk. And why divide by 6? Because we just want to find the internal variance of the numbers. We don't care about how many numbers we have, right? If you don't divide by 6, then the more number you have, the higher reference you get. And this is what we do not want, right? We just want to see if on average how the numbers diverge from the expected value, or how the numbers diverge from the average. We don't want to see like how many numbers there are. We just want to find the internal risk, right? So we find the internal risk, right? Do not want to care about how many numbers are there, right? So that's way so we normalize, right? We have a professional word for this. Divide by 6. It's called normalize. Because if you don't normalize, then if you have a 6 number, you sum up 6 stuff. If you have 10 numbers or 100 numbers, you sum up 100 times, and of course that will get a higher variance if you don't divide by 100, right? You have so 100 number, positive number summed together is of course or very likely to be greater than 6 numbers summed together. But we don't want to care about how many numbers are there. We just want to care if each number is diverged from the average number, right? So that's why we divide by 6. Okay. So that's the end of the lecture here. And let me stop share and stop recording.